amide. Amide has two resonance structures. Oxygen, which is more electronegative than carbon, would lead to the pi electrons being located specifically on O to form your O-, while nitrogen, which has a lone pair electron, will be used to form the pi bond between C and N. And in the process, nitrogen will become C+. And from these resonance structures, we can conclude that the nitrogen is no longer able to form hydrogen bonds because it no longer has a lone pair electron. The second conclusion we can derive is that the lone pair electron of nitrogen is no longer available to act as a proton acceptor. That's the reason why amide is not the base. And the C to N linkage, which is previously a single bond, has now become a double bond. Hence, the C to N linkage displays partial double covalent bond and therefore has restricted the rotation between C and N. So understanding the amide structures is therefore important to note that in terms of physical properties, amides are in fact neutral, and boiling points will still be high because they can form intermolecular hydrogen bond. However, third degree amide is not capable of intermolecular H bond since it does not have any electron deficient or protonic hydrogen. It's soluble since the C double bond O and the NH2 group could both form extensive intermolecular H bonds with water molecules. And again, tertiary amides will have lower solubility than expected because it lacks an electron deficient hydrogen. Let's take a look at the chemical properties. Chemical properties, as earlier explained, is neutral, so it's actually a fairly weak base. It's also a fairly weak acid, given that if it does donate a H+, then the conjugate base here will be highly unstable, given the fact that C double bond O is an electron withdrawing group that intensifies the charge. Next is that M- would have an extremely high charge density. So therefore, all the argument points towards the fact that the conjugate base is highly unstable, and hence it is actually a very weak acid. Next two reactions that which we previously have covered in our earlier sections in amine is the hydrolysis of your amides. And then the next one is actually the reduction of amide, which is a new area that we'll be focusing. So for hydrolysis of amides, these are some of the equations that we have. Do take a look and ensure that you are able to balance the equations accordingly. So next we take a look at the reduction of amide. So to reduce amide, imperative to note that we can only use lithium aluminum hydride in dry ether. It is a very strong reducing agent as well. NaBH4 aqueous and which is a weaker reducing agent, as well as hydrogen gas, both are not able to reduce your amide, similar to reduction of carboxylic acid. So if you reduce your 1 degree amide, you will find that what it does is that one of the oxygen is removed by reacting with 2 of the H to form water molecules, and thereafter 2 more hydrogen is added on to produce your amine. Same mechanism in terms for 2 degree and 3rd degree. So a quick recap for all the reduction reactions in the whole entire organic chem. Nitrile could actually be reduced, and these are all the 3 reducing agents that we have taught so far could be used to reduce nitrile to your 1 degree amine. Carboxylic acid can only be reduced by lithium aluminum hydride, similar to that of your amide. NaBH4 and hydrogen gas can't do the job. And for the other 3 reducing agents, they could reduce your aldehyde and ketone to form respectively your 1 degree and 2 degree alcohol. Finally, it's important to note that the conversion of nitrile to amine will see the compound gaining 4 hydrogen, ketone aldehyde to alcohol gaining 2 hydrogen, amide or carboxylic acid to amine and alcohol, primary alcohol respectively. You will gain 2 hydrogen and lose 1 oxygen. And for nitro to amine, that occurs in the reduction of your nitrobenzene to phenylamine. You will gain 2 hydrogen and lose 2 oxygen. And in that reaction, if you can recall, nitrobenzene going to phenylamine, you'll be using tin, con HCl in excess. And then after that, you have to add your excess NaOH to ensure that the product you get, which is originally NH2, but because of the presence of your HCl, it becomes NH3+. In the presence of excess NaOH to neutralize it, so that you will get back your phenylamine. Also do remember that ester can actually be reduced to form back the alcohol, and the carboxylic acid that's produced will be further reduced to primary alcohol. Let's take a look at some examples. In this reaction, as you can see, your acid chloride could now react with your phenol to produce your ester. It can actually react with your amine to produce your amide. Clearly, in this case, MbH2 is a stronger base than your alcohol. One could argue to say that nitrogen is bonded, although less electronegative, is bonded to 2 hydrogen, is better able to polarize both the lower electronegative hydrogen atoms. So consequently, N will become a lot more delta minus than your oxygen. And certainly, given that amine is actually a stronger base than your OH, then it's a more effective nucleophile. So therefore, it's better able to enable a faster rate of reactions with your acid chloride to actually produce your amide. Let's take a look at now the bond length between C and N. Before we look at some numerical data, so if X is an electron releasing group, then you will help to disperse the charge at the N+. If you help to disperse it, then it's going to make these resonance structures stable. If it's stable, then it's more likely for C to be doubly covalent bonded nitrogen, and hence because of that, you expect the bond energy to be higher and the bond length to be shorter. If Y is electron withdrawing, you help to reduce or disperse the negative charge on oxygen, stabilizing the resonance structures. So similarly, you will then have a higher CN bond, and therefore you will end up with a shorter bond length. All these arguments are presented in this information now, because if you now look at this structure, obviously relative to this is actually electron releasing, because alkyl is an electron releasing group. So clearly, you can see that the bond length is way shorter than compared to this. And certainly this is the shortest, because you'll find that there is actually 2 alkyl group releasing electron to nitrogen. So if it does that, it'll help to disperse and stabilize the N+. So and hence in this case, you can see that why the bond length of this is shorter than this. Finally, in this amide structure, it's actually an exceptional case, primarily because there's lots of steric hindrance. So you can't just look at the electron releasing effect from the alkyl group. But however, we are arguing from the fact that given its shape with respect to N, which is trigonal pyramidal, and also given the fact that there are a couple of cyclo rings within it with high strain energy, it's going to be causing this bond energy to be weaker, and therefore the bond length ought to be longer than expected. Finally, we're going to study the hydrolysis rate of the various amide. So one of the things to note is that clearly this carbon is delta plus, and you have your hydrolysis, which is a water molecule that will attack the carbon that is delta plus. And if the delta plus charge is intensified, for example, if your Y happens to be an electron withdrawing group, or your X happens to be electron withdrawing group, then we will be making this carbon more delta plus. Certainly in this example here, you can see that in the case of R1, which is actually here, if we do change the R1 group from a methyl group, with actually replacing one hydrogen with chlorine, so there's actually, so certainly Cl is an electron withdrawing group, and it will actually therefore intensify the delta plus charge, and in that case, the presence of the electronic Cl atom itself would have induced the carbon in carbonyl to be more delta plus, so rendering it more susceptible to OH minus attack during hydrolysis. So hence we expect the relative rate of hydrolysis to be faster than if a CH3 group is present. The next example that we look at is that we decide to replace this group with actually a benzene ring, and bonded to the benzene ring that will be 3Cl. Clearly the 3Cl will have electron withdrawing effect. However, one needs to note that the Cl atoms are significantly far away from actually the carbon in the carbonyl group. So therefore the effect, the electron withdrawing effect will be less pronounced. So we expect the relative rate of reaction to be actually between 1.5 to 5.